Thank you for the reminder. Okay, so in our normal definition of continuity, we say that f is continuous at the point C if, for every epsilon, there exists a delta, such that blah, 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 and I'll get to that in a second. But the point I want to emphasize here is that delta, of course, delta depends on epsilon. You've seen that in all the proofs you've done. But the thing I'm worried about is if you realize it also depends on C. Okay, so the quantity delta is allowed to change as you move along the function. And now I'll just put the rest of the definition here, such that if x minus c is less than delta, which again depends on epsilon and c, then the function values are within epsilon. Okay. Now, you might have noticed that sometimes delta doesn't actually depend on C. Okay. In the second problem of that homework that I'm still grading, you were allowed to just take delta equal to epsilon. Okay, there was no C in there. Many examples where it doesn't depend on C, although there are examples where it does depend on C. So the function x squared, your delta does depend on C in that proof of continuity. Okay, so there's something fundamentally different between different functions here. And so we have this notion of uniform continuity. And what uniform continuity does is, on one level, it's just going to move the quantifier. What it really does is it moves that point C, but then it eliminates this dependence on the point C in the definition of delta. So perhaps I should just state the definition. So this is our one definition for today. Continuity exists at a point. You're continuous at a point. Uniform continuity is about an entire set. Okay? So remember, in continuity, we say you're continuous on the set A if you're continuous at every point in A. Okay? Uniform continuity can only be for a set. So let's take a set. And we'll have a function with that domain. We say that f is uniformly continuous on A if, for every epsilon, there is a delta such that for all x and u in the set A, if x and u are within delta, then their function values are within epsilon. Okay. So this is a bit of a subtle change from our definition. Let's again look at what we've done. And in fact, let's go back up to the definition of continuity, and I'm going to change it to a definition of being continuous on an entire set A. Okay? So what did we used to say? The function f is continuous on A if for every point in there, for every u in A, and every epsilon greater than 0, there exists a delta which depends on epsilon and c, except now I've changed c into u. Such that, and I again want to change my c into u, just to try and match the book's definition in this section. Oh, such that. Benjamin says this is like the definition of quotient. Yes, very, very much so. Yes. And the whole thing is we've moved that quantifier. We've moved that for every point u in A. We've moved it down there. So, in the old continuity, it said, for all u in A, for all epsilon, there exists a delta such that x minus u less than delta implies f of x minus f of u less than epsilon. Okay. In uniform continuity, what we do is we take that for all a and u, and we move it right there. Okay, and since we're moving it past if there exists, if you want to think on this level, the definition gets harder to satisfy because the same delta has to work everywhere. Any questions about the definition?
So now our delta can epsilon is set as a whole?
Yeah, and it can only depend on epsilon. It cannot depend on the point you're at.
Right, okay.
Mm-hmm.
So the universal delta.
Yes. Okay. This is this is not the same definition. We have changed the definition because we moved to quantifier. Okay? This is a stronger definition. Now, I hope it's just obvious that if you are uniformly continuous, then you are continuous. Because uniformly continuous just says you can use the same delta wherever. Okay? Now, are there functions that are continuous on a set but are not uniformly continuous on a set? Indeed there are. Okay? Many functions are continuous but not uniformly continuous. With certain exceptions. So let's see how far we can get into this today. Okay. There's just a whole lot in this section, so I'm just giving up on any pretense that I'm going to cover the entire section. You should definitely read it. But I want to hit the highlights here. So, this is what the book calls the non-uniform continuity criteria. Okay. So what does it mean to not be uniformly continuous? Let's do the setup. The following are equivalent. 1. F is not uniformly continuous on A. Okay. 1 is what we want this result to be about. 2 is just going to be, let's go and carefully negate this definition. Okay, so what do we get when we negate this definition? The for all epsilon turns into a there exists epsilon. Okay, so I'm just gonna, there we go. Let's use this color. We've done that quantifier. And now we come to a there exists a delta. Okay? There exists a delta turns into a for all delta. Such that for every delta, okay, we've done that. And now the next quantifier we would hit would be this for all u. Okay. But then there's actually really, you think about what's inside here. We're saying for all u and x that are within delta. Okay. So what in the negation we're saying there exists an x and a u that falsify that condition on the inside. Okay. So there are points x and u in A within distance delta. So with x minus u less than delta, such that their function values are not close. Not being close means greater than or equal to epsilon. Okay, so there's no real content in saying that 1 and 2 are equivalent. 1 is saying, okay, the definition doesn't hold. 2 is we just went through the definition, we negated it. Okay, so there's really nothing to prove there. Okay, it's not the easiest definition in the world to negate, but we did it, okay? 3. 3 says, okay, if this holds, then what can we do? If 2 holds, then what can we do? Okay. You look at 2, it says that there's some delta, so that no matter how we choose delta, so there's some epsilon, sorry, so that no matter how we choose delta, we're going to have these points, okay? Let's let delta actually go to 0. Think about if we let delta go to 0. We find some epsilon. We take the epsilon from part 2. And now we're going to let that delta go to 0. what are we going to get? We're going to get points that are closer and closer and closer and closer together, but their function values always stay greater than or equal to epsilon. Okay? Now, we have language for talking about points that get. Okay, so what I want to say is when I say the points are getting closer and closer and closer, obviously you should say, wait a second, you're talking nonsense. Points don't move, right? What am I talking about? I'm talking about we'll get a sequence that gets closer and closer together. Okay, but it's actually two sequences. It's a sequence of x's and a sequence of u's. And those two sequences are getting closer and closer and closer, but their function values are not. Their function values stay epsilon apart. Okay? So, there exists an epsilon and two sequences. Okay. Saying that the sequences get close together just means the limit of their difference goes to 0. So I could say that's the distance between them, the absolute value of xn minus un. The limit of that is 0. Okay. But the function values don't get close. What does it say that the function values do not get close? Well, the distance between the two function values is always at least epsilon for every n. Okay, this is the first theorem in the book about uniform continuity, that these three things are equivalent.
Dr. Vader,
Mm-hmm.
how come we don't want to phrase this last line as a limit? That's like the distance between the functions. Wouldn't we also get a limit like this? So we have a limit y. Doesn't that translate to a limit n to f of x and f?
The maximum. But
So what we've written is stronger than a limit. Okay. A limit would say.
This is everything.
Yeah.
The limit would just include the tail.
Yes. Limits say things eventually hold. What we said is that it holds for every n. So that's stronger. Is that okay? And let me make one more point. I'm gonna fiddle with this just a tiny bit. When we say there, we said the limit of the distances between the x's and the u's is 0. This is something we proved way back, the first lecture on limits. Having a limit of absolute values being 0 is the same as just having a limit of things being 0. So we don't need the absolute value there. I erased something important. Okay. Instead of the absolute value, we just put parentheses. Cool. And also think about another thing we proved with limits. If that limit is 0, that is exactly the same thing as saying that the limit. Oh, okay. It's not exactly the same thing. If xn and un have limits, then this is saying that their limits are the same. Okay? But actually, this is a little bit more forgiving than saying that their limits are the same. because this does not say that they have to have limits. The sequences xn and un do not have to individually have limits for the sequence of differences to have a limit. Okay? We've done plenty of examples. I think we had an example like that in one of the successive problems or something. Or maybe in the quiz, right, where you could take two sequences that don't have limits, but their differences do have limits. Okay. I mean, just think about, you could have xn. Xn could be n, and un could be n plus 1 over n. Okay, two sequences that don't have limits, but their differences do have a limit that's 0. Okay?
I have a question though. If we were to negate just normal continuity, then there are points x and u and a would just go up to the front.
The u goes to the front. The x stays where it is. Does that make sense? So you negate normal continuity, it would say there is a point u at which you are not continuous. Okay, now then you take the negation inside that. There is a point u for which there is an epsilon, such that no delta works. Okay, and then you would propagate the negation inside there.
Right. Okay. Thanks.
So in normal continuity, that point u is always at the front, and in uniform continuity, the point u is always in the back. Okay, and again, based on the homework that I'm going to finish grading today, I think that a lot of you have been thinking in your heads about continuity as if it's uniform continuity, and it is not. Okay, now, in a good lecture on uniform continuity, you would think I would do some examples before I just launch into theorems. The thing is, I would like to do the theorems because then the examples just become obvious. Okay. So this is what not uniform continuity means. Now I want to do a theorem about what uniform continuity means, and then I will have some examples which we won't actually have to work out because we'll just see them from the theorem. Okay. So here is the book just calls this your uniform continuity theorem. Let I be a subset of the real numbers, and you probably know what's coming because I used the letter I. It's going to be an interval. But more than that, it's going to be a closed and bounded interval. Okay. Last couple lectures. Yes, go ahead.
Okay. Does it have to be? Can it be empty?
Yep. Yep. Thank you for checking. You'll see. Empty would be fine. Okay. So our domain is a closed and bounded interval, and the theorem says if we're continuous, then we're uniformly continuous. Okay, so this theorem gives you infinitely many examples of uniform continuity, right? Take any nice function, take a closed and bounded interval. There you go. That's an example of uniform continuity. Okay. On the other hand, you take a continuous function, take something that's not a closed and bounded interval, it's not necessarily uniformly continuous. Okay? You have to be a little bit skeptical there. And we'll see examples of that in a minute. I'm aware that we only have 15 minutes. Let me think. Can we prove this in that time? I think we can. But what we can't do is write a really nice proof with sentences and things. So instead, I'm going to call it a sketch of a proof, and we will just write some notes. Okay? Why is this true? Suppose not. Okay, so F is not uniformly continuous. Uniformly continuous, those are two relatively long words. You will frequently see me write just this abbreviation. You're welcome to do that as well. Okay. Okay, so suppose F is not uniformly continuous on I. Well, we got this theorem up here. We're going to use part 3. So, there exists an epsilon greater than 0 and these two sequences, xn and un, in I, that's key, such that their limits are 0, such that the limit of their differences is 0, but the function values remain at least epsilon apart. Okay, this is a proof by contradiction. So what are we trying to contradict? We're going to contradict the assumption that F was continuous. Okay.
I was wondering about, excuse me, sorry for interrupting, but I was wondering about the whole limit x n minus un thing, like, why specifically 0?
Because 0 is the only number that means you're getting close together.
Oh, right, I remember now, thanks.
Cool.
Like,
Okay.
I recall you saying something like that, but can't believe I forgot about that, but thanks for reminding me.
Good. Okay, so we use that theorem. Now I've scrolled away, the theorem's gone. This is what we're taking away from it. We want to get a contradiction to the fact that F is continuous. Okay. Now, you think back to the last lecture that we did on Monday, and in fact, I think the lecture before it as well. This comes up all the time. We got some sequences on a closed and bounded interval. We get to hit them with Bolzano-Weierstrass. Okay. Bolzano-Weierstrass, that works on any bounded interval actually, and it says you get a subsequence that converges. Okay, but then if you take Bolzano-Weierstrass and you do it on a closed and bounded interval, then not only do you have a subsequence that converges, that subsequence converges to a point in the interval. Okay, that's what closed gets you. Okay, it's exactly like both both proofs we did on Monday. Okay? So I'm going to say by Bolzano-Weierstrass, there is a subsequence xnk that converges to some point x star in the interval. Okay? Again, that's Bolzano-Weierstrass just needs bounded, but if you want the limit to be in the interval, you also need closed. Okay? Now, you look at that subsequence. The corresponding u's, and by that I mean I take the same indices in the u's. That subsequence must also converge, and must also converge to the same thing. So, what would the subsequence of the u's be? It would actually be UNK, okay? Because the way this works, n sub k got defined in the previous sentence. That is just some choice of indices. So when I put the same indices on the u, okay, I get the corresponding subsequence. So this sequence, u and k, must also converge to x star. Okay. However, the distance between f and k, f of x and k, and f of u and k is at least epsilon for every k. Okay. Now, you think about the sequential version of continuity says you take a sequence of function values. Sorry, you take a sequence of x values, and the sequence of function values has to converge to the limit. Okay. But so our contradiction here is, but since f is continuous, we assumed f was continuous. We have f, the sequence f of x and k, f of x and k, that has to converge to f of x star, and the u's, the f of the u's has to converge. And that's a contradiction.
Professor, where did we is continuous? I think it's not uniformly.
I'm sorry, my internet is really bad today. So you broke up a little bit there.
Where did we assume f is continuous?
Right. So I'm writing a little bit of a sketchy proof. When we say suppose not, we are what I mean there is we're supposing that this is true. F is so I is a closed and bounded interval, and f is continuous on I. And however, f is not uniformly continuous on I. And then we're deriving a contradiction.
Dr. Vader,
Mhm.
can you justify this UN star a little more?
Can I justify which part? The convergence of the function values, or?
No, A converges to X star.
Oh, yes.
We must also converge.
Okay.
I think it just
Sure.
follows from the properties of limits, right?
Yeah, or you can do this triangle inequality trick. Okay? So look at the distance between U and K and X star. Now let me throw in an X and K in there. This is this is our standard trick. And now let me triangle inequality that. Now you got two quantities there on the right that both go to 0. Right? The u minus x goes to 0 because that's how we've said that the u's and the x's go to 0. So the distance between the u's and the x's go to 0. That's right there. And then the x and k minus x star part goes to 0 because x and k is converging to x star. Yeah.
Okay.
And therefore u and k minus x star goes to 0. And that's precisely what we said over here. Okay? Now, the reason I wanted to rush through that proof, and that is the end of the proof, we've got a contradiction. We contradicted the sequential definition of continuity. Okay? So again, that's infinitely many examples. And so basically, you're going to be uniformly continuous if your domain is a closed and bounded interval, or if your function is really stupid. Okay? Constant function, linear function, anything like this, that's going to be uniformly continuous. Anything more exciting, like even x squared, it's going to be uniformly continuous when your domain is closed and bounded. Okay. Note this. If f is uniformly continuous on I, then it is also uniformly continuous on all subsets. Okay. Why is that true? Well, you just go look at the definition. It's clear that if you're uniformly continuous on a superset, then. Okay, so I guess I should say you also get all these functions that are uniformly continuous because the domain is contained in a closed and bounded interval on which they are continuous. Okay, now this statement actually kind of has a converse in some sense. Okay. To get to that, we need another theorem. 5.4.7 in the book. And I believe it was, yes, Benjamin said that our definition of uniform continuity reminded him of Cauchiness, and this is your connection for uniform continuity and Cauchiness. If F is uniformly continuous, and Xn is Cauchy, then you get something really nice. The function values are also Cauchy. Okay. The proof of this is very easy. You should definitely read it in the book. It's just not quite easy enough to do in 30 seconds. Okay. Now, using this theorem, you get a theorem called the continuous extension theorem. And this is where I'm going to stop. I'm just going to state this theorem. And this is, in some sense, the converse to that note I made just above. If F is uniformly continuous on an open interval, on a bounded open interval. So a bounded open interval is just the open interval from A to B. And in fact, I want to make this an if and only if, and I didn't start it out right. So let me rewrite the beginning. The function f is uniformly continuous on the open interval a, b, if and only if it can be defined at a and b to make it continuous on the closed interval a to b. Okay. Now, in terms of just the theory and how things fit together, the continuous extension theorem is, I think, very pretty, and it's obviously the bigger of the two. In terms of doing homework problems, this Cauchy thing is incredibly important and incredibly useful. Okay, so yeah, Benjamin, that's essentially what we're saying in the continuous extension theorem. They have to be removable singularities. So let's look at just one example, and that'll be the end of today's lecture. Let's look at f of x equals 1 over x on the open interval, say 0 to 1. Okay? Could that possibly be uniformly continuous on that interval? You look at the continuous extension theorem, and it seems to suggest no, that's probably not going to be true, right? Because there's no way to define that function at the point 0 in a way that it will make it continuous. 0 is not a removable singularity for that function. Okay? But you think about, if this was actually a homework or a quiz problem, how are you actually going to write that argument that I just gave? You should instead go to this theorem 5.4.7. Okay? If it were, okay, then since the sequence 1 over n is Cauchy, the sequence f of 1 over n would be 2. Would also be Cauchy. Is the sequence f of 1 over n, which is the sequence n, is that Cauchy? Right? No. Terms aren't getting close together. So, and It is not. So the function 1 over x is not uniformly continuous on the open interval from 0 to 1 because the sequence of function values of a Cauchy sequence here. We picked whatever Cauchy sequence we wanted. The sequence of function values is not Cauchy. So it can't be uniformly continuous. Okay, so I hope I convinced you that the theorem you really need to have available to use on homework problems is that 5.4.7. Take a Cauchy sequence. The sequence of function values has to be Cauchy as well. Okay, so I ran a few minutes over. That is the end of our lecture. I will stick around for any questions that you might have.